So you can write down power counting formulas like we did in Kyle perturbation theory. Maybe I'll just write those formulas down. So in general, in Kyle perturbation theory, we had a formula that said if we want to figure out the power counting of any given diagram, we can have a counting for that diagram and we know what size it is. And there's analogous formulas like that in both SCET1 and SCET2. So in SCET1, it's pretty simple. You say you have something that's order lambda to the delta, then delta, the formula for it is the follows. This is very analogous to what we talked about for Kyle perturbation theory. So these guys here are vertices that are purely ultrasoft. And if you have purely ultrasoft vertices, you're subtracting 8 because the measure of the ultrasoft particles is 8. I'm not deriving this for you. I could, but I think it's fairly intuitive. So if you think about the lowest order Lagrangian, say psi bar ID slash psi for ultrasofts, this would already be something that's lambda to the 8. And this is then leading order, so you subtract 8. And this guy here is the rest. This is sort of anything mixed or purely collinear. And then for that guy, you subtract 4, because as soon as you have at least one collinear particle, then you have to use the collinear measure. And so here, some operator like c bar n dot dc was order lambda to the 4. So you subtract 4, and that's leading order. And so what this formula allows you to do is really just, you do power counting entirely in terms of vertices. You never have to power count measures for loops or power count propagators. You just count vertices. So if you want to know how big a time order product is, and it's a time order product of an L3 with an L2 with this kind of setup, this will be basically, you count this as lambda 5. And you could even get the sort of absolute size right, taking into account the scaling of external particles. And that's what this sort of constant prefactor does. And u is equal to 1 only for pure ultrasoft. Otherwise, it's 0. OK, so there's formulas like this. And there's an analogous one in SCET2, which is a little more complicated. But it allows you just to have a power counting where you can just power count Lagrangians or operators. O1 with L1, and then that's lambda squared, without having to worry about kind of what propagators do I have in this time order product, what loops do I have. You never have to ask those questions. You just have power counting at vertices. And that makes things quite easy.